Hello, everyone! In the previous lesson, we learned about the disassembly of a three-phase asynchronous motor. It includes the following. 1. Disassembly of three-phase asynchronous motor. 2. Safety precautions for the disassembly of a three-phase asynchronous motor. Today, we are going to continue with the assembly and disassembly of a small power three-phase asynchronous motor. We are going to learn 1. Structure of small power three-phase asynchronous motor. 2. Operating principles of three-phase asynchronous motor. Let's start with Part 1. Structure of small power three-phase asynchronous motor. It mainly consists of two parts called stator and rotor. The structure is shown in Figure 6.2.6. 1. Stator. A typical stator consists of three major parts, namely stator frame, stator core, and stator winding. The frame is usually made of cast iron or cast steel, and the central iron core has the shape of a cylinder made from thin silicon steel laminations assembled together. There are several evenly spread out parallel slots on the inner circle of the central iron core, and the stator winding is installed in the slots. The stator winding is the circuit of a motor. The stator winding of a three-phase motor is composed of symmetrical three-phase windings. The three independent windings are stacked in the stator slot, spatially oriented 120 degrees apart. The starting ends of windings are U1, U2, V1, V2, W1, and W2, respectively, and are let out from the junction box on the frame. According to the requirements, the three-phase stator windings are connected in a star or delta, and the specific wiring method is shown in Figures 6.2.7a and b. If the stator windings are connected in a star, the voltage across each phase winding is called the phase voltage of the power supply. If the stator windings are connected in a triangle, the voltage across each phase winding is called the line voltage. The specific method of connection depends on the rated voltage value of the motor. For example, if the rated voltage is 220 volts, then the motor should be connected in star. If the rated voltage is 380 volts, then the motor should be connected in delta. 2. Rotor. A typical rotor consists of three major parts, namely rotor core, rotor winding, and rotor shaft. The iron rotor core is also made from thin silicon steel laminations assembled together and fixed on the rotor shaft. There are also several evenly spread out parallel slots on the outer cylindrical shaft of the rotor. The rotor winding is installed in the slots. The rotor winding is basically divided into two types depending on its structure: squirrel cage type and wire wound type. 1. Squirrel cage rotor. A squirrel cage rotor is a type of rotor in which a bare wire is inserted into each slot of the rotor core. Two short-circuit rings are used to connect the wires at both ends of the iron core to form a closed short-circuit winding. If the iron core is removed from the stator, the winding shape is like a squirrel cage. Therefore, it is called a squirrel cage rotor. Cast aluminum cage rotors are generally used in small and medium-sized motors, whereas copper conductor rotors are generally used in large-sized motors, as shown in Figure 6.2.8. 2. Wire wound rotor. A wire wound rotor is a type of motor in which symmetrical three-phase windings are embedded in parallel slots and their endings are connected in a star. The starting ends are connected to three insulated slip rings on the rotor shafts. The windings are connected to the external circuit through a brush. This type of motor is called a wire wound motor, as shown in Figure 6.2.9. Next, we'll continue with Part 2, Operating Principles. Figure 6.2.10 below is a demonstration of the experiment for the rotating principle of a cage asynchronous rotor. A conductive cage rotor is placed between the two poles of the horseshoe magnet with a handle. When the horseshoe magnet is rotated by rotating the handle, it is found that the cage rotor will rotate with the horseshoe magnet. The faster the magnet rotates, the faster the cage rotor. If the magnet is rotated in the opposite direction, the cage rotor will rotate in the same direction as well. In the above experiment, first of all, a rotating magnetic field is established due to magnetic rotation. The cage rotor follows the rotating magnetic field. This suggests that a rotating magnetic field should be established to drive the rotor. In addition to producing a rotating magnetic field by rotating a permanent magnet, a rotating magnetic field can also be established by supplying three-phase AC to the stator winding. The simplest stator model is shown in figures 6.2.11, where the planes of three identical coils are physically placed at a 120 degrees angle from each other. When a star or delta connection is adopted and in a three-phase AC circuit, the small magnetic pin in the coil will continuously rotate. The small magnetic pin will point in the opposite direction when the two-phase firewires are exchanged with each other. This suggests that a rotating magnetic field is produced in the stator current space, which can rotate the rotor after being placed in the rotor. A three-phase synchronous motor can operate at a synchronous speed or a motor speed. Synchronous speed refers to the speed of the rotating magnetic field, denoted by N1. The rotor speed is the speed of the motor on the nameplate, denoted by N. The above experiment suggests that it is necessary only to exchange two firewires in order to change the direction of rotation of the magnetic field, thus changing the direction of the motor. It is necessary only to increase the synchronous speed in order to increase the rotor speed. The synchronous speed of an AC motor is determined by the frequency of the source and the number of poles. The table below gives the number of poles and synchronous speeds for a power frequency of 50 Hz. 3 safety precautions for a three-phase asynchronous motor. 1. The phase loss of a three-phase asynchronous motor is a frequently occurring trouble. This occurs when there is poor contact, a broken power line, or fuse blow, etc. External manifestations include a decrease in speed, abnormal sound, and an increase in current, which may easily cause the motor to burn out. 2. The overload operation of a motor will cause a decrease in speed and an increase in current. Excessive heat occurs over time, which will accelerate the aging of winding insulation and reduce the service life. Severe overload may even cause rotor blockage and burn out the motor. 3. When the voltage is too high or too low, or in case of incorrect winding wiring or short circuits, the motor will begin to overheat and cause rapid deterioration of the winding insulation within motors or even burn out the motor. The content of this lesson has been fully presented. Let's review the key points of this lesson. 1. Structure of small power three-phase asynchronous motor. 2. Operating principles of three-phase asynchronous motor. That concludes this lesson. Thank you, everyone.